Hello, this is checkpoint 2.47. They want us to find an equation of a plane that contains the two lines. So let's write those lines down first. We have L1, and let's see if we can write it in parametric form, because that's a more useful way of writing it. So if we imagine that those are all equal to t, then we have x is equal to t, y is equal to negative t, and z is equal to t. So that's L1. And then L2 would be, if the first one was equal to t, then it would be 2t plus 3 is equal to x. So x is equal to 2t plus 3. Just kind of solving for x there. And then if we solve for y, it's just by itself. Y is equal to t. And then z, if we solve for z, z is equal to t plus 2. This is a z. So those are our lines. And let's take a look at the scenario that we have here. We have these two lines. I'm assuming they intersect. I don't think I'm interested in checking that. But this is L2 line and L1 line. And the place they intersect is not really that important. But what they are saying is that these two lines lie on the same plane. Well, these two lines have direction vectors. Let's call that direction vector D1, and the other one has a direction vector we'll call D2, and those direction vectors are flat on the plane. So if you have some direction vectors that are flat on the plane, if you cross them, you're going to get a vector that's perpendicular to both of them. So that is going to be one of the important things that we need from an equation of a plane. So for an equation of a plane, we need a point and a normal. Now, a point can be found by any of these points. You can find a point on L2 or L1. So we have freedom with that point. But to find a normal vector, you have to take the cross product. So we can extract a point from P1 or from L1. Let's just say point from L1, and that's just the constants that are in x, y, z, and in this case it would just be zeros. We can also extract a point from L2, and that's going to be given by the constants again. So it's 3, 0, and 2. We can use either of these points. We're just going to use one of them after we figure out the normal, and then we'll talk about the equation of the plane when we get there. All right, to find a normal vector, we're going to do the cross product. We'll call it n, and it doesn't matter which way you cross it. Our normal vector could be going up or down from the plane, and it doesn't really matter. So this is a cross product of D1 and D2. And we haven't identified D1 and D2 yet, but you could probably pull it out already, just in case they're the coefficients of the t. So let's just make a note. D1 equals 1, negative 1, 1. And D2 will be equal to 2, 1, 1. Okay, and we can use either order. But when we set up our cross product, it'll be I, J, K. And let's put D1 first. 1, -1, 1, and 2, 1, 1. So the cross product here in the I direction would be -1, -1. So that's -2. In the J direction, it'll be negative. And then we have 1 minus 2. So that's -1. Make that to a plus. That's a 1. And then in the K component, it would be 1 minus -2. So that's +3. So it'll be 2, a 1, and a 3. Okay. Now to find an equation of a plane, what we need to do is we randomly pick a point, and either of these points would work. So we have a point, and then we can connect another generic point, x, y, z, on the plane with that given point. And let's just go through the motions of creating this equation of a plane. So we have a generic point x, y, z, and we can call this a point or a vector. And we're going to subtract whatever point that we found on the plane. Let's call it x naught, y naught, z naught. And by x naught, y naught, z naught, I mean it's either one of these two. And we're going to dot that with the normal vector. And because this vector that connects these 2 points, these 2 points are supposed to be on the plane, and so when you subtract them, then you'll get a vector that's still on the plane, and this normal is supposed to be perpendicular, so when we take the dot product, it should equal to 0. So it'll be the dot product of n dotted with x, y, z, and I'm doing one of the distribution rules for the dot product, and then we have a minus n. Also, the dot product is commutative, so I'm doing some other stuff. We're switching it into an actual point. And remember, the actual point, we found 2 of them, so we just need to use one of them, and this is equal to 0. So another way to rephrase the dot product, or the area, or the equation of the plane, is going to be the normal dotted with the generic x, y, z variables equals n dotted with the normal vector dotted with one of these random points. And by random, I mean they're actual points on the plane. Okay. All right, so this is where we're going. We found our normal vector. This is n, our normal vector. And when we dot this with x, y, z, it'll just be each of those components multiplied by x, multiplied by y, and then multiplied by z. And then likewise for the right-hand side, it'll just be this dotted with one of these points. And so let's try that. It'll be -2 times x and plus 1 times y plus 3 times z. So that's the left-hand side. And then we dot this with one of these points, and one of them is 0, so I would love to use that. But if you decide you dot it with this, notice that you should get the same answer. That -2, 1, 3 dotted with 3, 0, 2. What's that? That's -6 plus 0 plus 6, which is also equal to 0. So either way, you're going to get, as long as that, that point is on the plane, you're going to get the same answer. Okay, so this is our equation of our plane that contains those 2 lines. Okay, I hope that helps.